Good day, class, and welcome to our first lesson in organic chemistry. You started doing organic chemistry in Form 5, where you were taught about the hydrocarbons. You were taught about the aliphatic hydrocarbons, to be precise, alkanes, alkenes, and alkynes. In OPSEED, we are going to go further into the hydrocarbons. And for our first lesson today, we are going to be treating hydrocarbons. Like I earlier said, hydrocarbons are compounds containing carbon and hydrogen only. There are basically two main types of hydrocarbons, namely aliphatic hydrocarbons, otherwise known as straight-chain hydrocarbons, and aromatic hydrocarbons, also known as arenes. Aliphatic hydrocarbons are hydrocarbons in which the carbon atoms are arranged in a straight chain. That is, there are no rings within the carbon atoms. These aliphatic hydrocarbons include alkanes, alkenes, and alkynes. For our first lesson today, we're going to begin with alkanes, without which, let's first of all look at what aromatic hydrocarbons is all about. Aromatic hydrocarbons, also known as arenes, are hydrocarbons in which the carbon atoms are arranged in a straight chain structure. For example, benzene. It is often called the benzene ring. It is made up of 6 carbon atoms arranged in a ring structure. There are 2 types of hydrocarbons. That is, aliphatic hydrocarbons. Aliphatic hydrocarbons, like I earlier said, are made up of alkanes, alkenes, and alkynes. And we said aliphatic hydrocarbons are hydrocarbons in which the carbon atoms are arranged in a straight chain. Aliphatic hydrocarbons are also called straight chain hydrocarbons. And we said there are 3 types of aliphatic hydrocarbons: alkanes, alkenes, and alkynes. The next one we are going to look at is aromatic hydrocarbons. Aromatic hydrocarbons, that is benzene. Aromatic hydrocarbons are also called arenes. Here, in aromatic hydrocarbons, the carbon atoms are arranged in a ring structure. Like you can see from the example I'm going to place up now, we say aromatic hydrocarbons are hydrocarbons in which the carbon atoms are arranged in a ring structure. Meaning that what? Like I said, you see from the structure, let me take an example. Aromatic hydrocarbon, let's take benzene. You have, I said they have 6 carbon atoms in the benzene ring, and it forms this ring structure as such. You can see fine. That is a benzene structure. Another example we're going to look at is under aliphatic hydrocarbons. I draw the structure. You see that it is a straight chain. There is no ring. Even if the straight chain is branched, even if it has branches along the line, but you wouldn't find any ring structure, giving rise to the name aliphatic or straight chain hydrocarbon. Like you can see, let's take for example butane, or rather we should take a 6 carbon structure like hexane. This we are going to draw now is a aliphatic hydrocarbon, to be precise, an alkane called hexane. That is are hexane. We have benzene. This is benzene, the benzene ring, and here is hexane. Hexane is an alkane. From there, we'll be going straight into our aliphatic hydrocarbons. And under aliphatic hydrocarbons, we are going to treat alkanes, alkenes, and alkynes. But for our lesson of today, we'll be doing we're going to be doing alkanes. We'll begin with alkanes. And we're going to see that alkanes are straight chain hydrocarbons, and they have the general molecular formula CnH2n plus 2. Alkanes are also saturated, meaning they contain the maximum amount of hydrogen atoms and no multiple bonds between carbon atoms. Each carbon atom in these alkanes is sp3 hybridized and tetrahedrally surrounded by hydrogen and other carbon atoms, meaning that what? Each carbon atom in an alkane is sp3 hybridized. And also, when we say an atom is sp3 hybridized, meaning it has a tetrahedral structure being surrounded by 4 other atoms. Alkanes have single bonds between carbon atoms. What we are saying here is alkanes do not have multiple bonds between carbon atoms. But as we go further, you see that alkenes have double bonds, alkynes have double bonds. Like you earlier saw from the example of aliphatic and aromatic hydrocarbons, you came to see that benzene, the example I placed on the board, has double bonds between the carbon atoms. Alkanes, they form a homologous series of saturated hydrocarbons with general molecular formula CnH2n plus 2. Saturated means they contain the maximum amount of hydrogen atoms and no multiple bonds between carbon atoms. Each carbon atom is sp3 hybridized and consequently tetrahedrally surrounded by hydrogen atoms and other carbon atoms. Still under alkanes, what we are going to look at here is isomerism. You did isomerism when you did organic chemistry in Form 5. So I would like you to try and recall what your teacher taught you isomerism is. Isomerism is the existence of 2 or more molecules having same molecular formula but different structural formulas. Alkanes undergo structural isomerism. That is, isomers are due to the branching of the hydrocarbon chain and are thus chain or branched isomers. If I may ask, what kind of isomerism do alkanes undergo? Like I said, alkanes undergo structural isomerism. And when you undergo structural isomerism, the type of isomers that result from structural isomerism, it is either chain or branched isomers. When we talk of chain or branched isomers, chain means the long chain as a straight chain. Branch means you can take the long chain and you branch it off to give you another compound. But this same compound that has been produced from the initial compound is going to have same molecular formula but different structural formula. Let's take this example we are going to look at. Let's take the example of hexane. Hexane has 6 carbon atoms. Like you can see, CH3, CH2, 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 CH2 again, and CH3. This is a normal hexane. N-hexane. N-hexane meaning that word, it is a normal hexane structure. And this is the formula of hexane. You have the formula of hexane as C6H14. Is that okay? Now, let's look at the isomers that are going to result from hexane. Like you can see, we're going to have this. We're going to have this. Let's just draw and result to it. So far we've drawn 4 carbon atoms. Now we're going to see this. Fine. This now, how can you call this structure? Definitely the longest chain there, if you can count, this is 1 carbon, 2 carbon, 3 carbon, 4 carbon. But now you need to take the shorter direction. This is 1 carbon, 2 carbon, 3 carbon, and carbon 4. Okay, let's take, from now we're going to take from the right to left, which means we are going to use our carbon 1. And on our carbon 1, we have how many methyl groups attached to it? This is a methyl group 1. This is another methyl group 2. This now, we're going to look at it to be as 1, 1, indicating that there are 2 methyl groups attached on carbon 1. So we're going to say 1, 1, dimethyl. 1, 1, dimethyl what? 1, 2, 3, 4. The 4 carbon atoms, which means 4 carbon atoms refers to butane. Now we have 1, 1, dimethyl. 1, 1, dimethyl butane. That is a structure. This is a branch isomer. Another structure we can have is this. Making the longest chain to be 5 carbon atoms, and we put this here. This one, we realize it is going to be, let's count from the left. 1, 2, 3. First on carbon 3. 1, 2, 3. Still first on carbon 3. Which means it's going to be 3 methyl, 3 methyl, what? 3 methyl pentane. 5 carbon atom is pentane. So now that we have as an example, as we go further, you understand more of what we're trying to say. Like we said earlier, we said isomerism is the existence of 2 or more molecules having same molecular formula but different structural formulas. Like we've seen from the example there, we saw the example using hexane, we saw the various isomers of hexane, we saw the chain isomer, and we saw the branched isomer, all of which fall under structural isomerism, indicating that all alkanes undergo structural isomerism. And we realize that the first 3 members of alkanes, that is methane, ethane, and propane, do not have isomers. But from butane upwards, we realize that each of the higher member has a progressive greater number of isomers. For example, butane has 2 isomers. Pentane has 3 isomers. Hexane has 4 isomers. Heptane is going to have 5 isomers. and so on and so forth. So that is how it goes. Okay. The isomers. The isomerism in alkanes is structural isomerism. All isomers are due to branching of the hydrocarbon chain and are therefore chain or branched isomers. The first three members, like I earlier said, that is methane, ethane, and propane, have no isomers, but butane has 2 isomers. Pentane has 3 isomers, and each of the higher member has a progressive greater number of isomers. For example, let's take butane. The first example, butane. You see that the first structure, you can see from your screen, the first structure we're going to have there is N-butane, showing that butane has the longest structure there, the longest chain is 4 carbon atoms. These 4 carbon atoms, if branched off now, 4 carbon atoms branched off, you get off one methyl group and place on the second carbon atom. The longest chain there is going to be propane, 3 carbon atoms, giving the name 2-methyl-propane, otherwise known as isobutane. Butane has 2 isomers, N-butane and 2-methyl-butane, also known as isobutane, like I earlier said. 2-methyl-propane, because the methyl group is attached on the second carbon atom. Pentane has 3 isomers, that is N-pentane, 2-methylpentane, and 2,2-dimethylpropane, also known as neopentane. 2,2-dimethyl because there are 2 methyl groups attached on the second carbon atom. Like you can see on the board there, we said the first isomer of pentane is N-pentane. The next one is 2-methylbutane. And the third one is 2,2-dimethylpropane, otherwise known as neopentane. The next subheading we're going to look at is sources of alkanes. Alkanes can be obtained from the laboratory by either addition or substitution mechanisms. Industrially, the main sources of alkanes is by fractional distillation of crude oil and by destructive distillation of coal and natural gas. The first thing we're going to look at there is how can we obtain alkanes from the lab. The first method we have there is hydrogenation of alkenes, that is addition of hydrogen to alkenes. As we go further, we're going to see more. The major sources of alkanes is by destructive distillation of coal, natural gas, and fractional distillation of crude oil. They can be prepared in the lab, that is in the laboratory, by either addition or substitution mechanisms. The first subheading we're going to look at there on how to obtain alkanes from the lab is by hydrogenation of alkenes, that is addition of hydrogen to alkenes. Hydrogenation is the addition of hydrogen. Alkenes are unsaturated, thus when they undergo addition of hydrogen, they yield alkanes. Hydrogenation takes place in the presence of platinum or nickel or palladium catalyst, depending on the temperature of the reaction. Platinum and palladium functions at room temperature and pressure, that is at 25 degrees Celsius, while nickel functions at 140 degrees Celsius and slightly above. Let's see now. Hydrogenation of alkenes. This is the most important method of preparing specific alkanes. The alkene with same number of carbon atoms with the alkane to be synthesized is hydrogenated. In this method, a mixture of alkene and hydrogen is passed over finely divided platinum, nickel, or palladium catalyst to yield the corresponding alkane. Like from the general example you see there, we have alkene CnH2n plus 2, CnH2n plus hydrogen, the presence of platinum, nickel, or palladium catalyst to give us CnH2n plus 2. The catalyst functions by absorbing the reactants on its surface where they come in contact for the reaction to take place. Like the specific examples there, let's see how we can prepare propane. C3H6, that's propane, plus hydrogen. We use platinum or palladium catalyst at 25 degrees Celsius. It's going to yield us our propane, C3H8. The next example we're going to look at there is how we prepare this same propane from propene using nickel catalyst. And the temperature there will be 140 degrees Celsius, like you can see on your screen. And that is it. The next method of obtaining alkanes. Alkanes can also be obtained by reduction of halogenoalkanes. Halogenoalkanes are otherwise known as alkyl-halides, also known as alkyl-halides. Halogenation of alkanes means that word, halogenation. Halogenation. When we talk of halogenation, that is addition of halogens. But now we are talking of reduction of halogens, of halogenoalkanes. Reduction meaning the removal of the halogen from the alkanes. They can be prepared from halogenoalkanes by Würtz synthesis. The halogenoalkane is mixed with metallic sodium in anaprotic ethoxyethane. Like you can see from the example there, we have two sodium halide. We have two halogenoalkane there, not specified. X stands for halogen and R stands for alkyl group. Plus 2 sodium is going to yield us our 2 alkanes in the presence of ethoxyethane. Look at the specific example there. Chloroethane plus 2 sodium plus chloroethane in the presence of ethoxyethane is going to yield us butane. This method is also known as coupling of halogenoalkanes. Like the second example said, you can see that from the second example, 2 molecules of chloroethane are reacted to 2 molecules of sodium. That is 2 molecules of chloroethane reacted with 2 molecules of sodium. The product is butane, indicating that the 2 ethyl groups have been coupled to form butane. Halogenoalkanes can also be reduced through Grignard reagents to yield alkanes. This involves mixing a halogenoalkane and clean magnesium filings in ethereal solution. Ethereal solution is a solution of ether. In ethereal solution, like you can see from a specific example there, we have the example there. First one is how to obtain our Grignard reagent. A Grignard reagent is a mixture of alkyl, that's alkyl group, manganese, and a halogen. Like you can see, halogenoalkane plus magnesium in the presence of dry ether, that's ethereal solution, to give us our Grignard reagent. When the reagent is treated with aqueous solution of hydrochloric acid or sulfuric acid, the alkane is formed. See from the example there, we have a Grignard reagent in the presence of water that is being hydrolyzed. The presence of hydrochloric acid is going to give us an alkane plus magnesium hydroxide halide. By specific examples we can see there. The specific examples we could see there, we saw that they had the Grignard reagent contained a methyl group. Methyl group in the presence of magnesium and iodine, that's the iodide ion, plus water being hydrolyzed in the presence of hydrochloric acid, aqueous hydrochloric acid. It's going to give us methane plus magnesium hydroxide and iodine present in that compound. The halogenoalkane can also be reduced by nascent hydrogen. The nascent hydrogen is produced by dipping zinc in dilute copper sulfate. So the nascent hydrogen is produced by dipping zinc in dilute copper sulfate. The solution, known as zinc copper couple, is mixed with water and ethanol to produce hydrogen. See from the example below there, halogenoalkane zinc copper couple in the presence of alcohol to give us alkane plus hydrogen halide. Chloromethane is going to give us methane plus hydrogen chloride. Now, the next topic we are going to look at, the next method of obtaining alkanes we are going to look at is decarboxylation. When we talk of decarboxylation, we mean the removal of carbon dioxide. In this case, it is the removal of carbon dioxide from a sodium salt of carboxylic acid or carboxylic acid with soda lime. Soda lime is a mixture of sodium hydroxide and calcium oxide. Decarboxylation of sodium salt of carboxylic acid or carboxylic acid with soda lime, which is a mixture of sodium hydroxide and calcium oxide. Examples, we have sodium ethanoate plus sodium hydroxide in the presence of heat gives us methane plus sodium carbonate. Methanoic acid in the presence of soda lime and heat is going to give us methane plus carbon dioxide. The next example there is methanoic acid in the presence of soda lime and heat is going to give us hydrogen gas and carbon dioxide gas given off. In our next class, we've come to the end of our class for today. In our next class, we're going to be treating the physical properties of alkanes, the reactions of alkanes. We're going to see the various types of reactions of alkanes. What kind of reactions do alkanes undergo? We're also going to see another class of alkanes, which is cycloalkanes. Cycloalkanes are alkanes in which the carbon atoms are arranged in a ring structure. Thank you and see you next class.